Welcome to Closing the Loop, a podcast presented by Lakeside Process Controls, where we connect you with experts, end users, and suppliers in the industrial automation industry. My name is 𝗧𝗜𝗘𝗦, Business Unit Lead for Measurement Solutions and host of the show. Each episode will be featuring special guests from Lakeside, Emerson Automation Solutions, and other industry leaders. We hope that through these conversations, we can close the loop between your current knowledge and the latest advancements in industry. Our goal is to educate you, provide you with ideas for improving efficiency and safety throughout your facility. And with that, I'd like to introduce you to today's guest, Mo Fazl.
Thanks. It's nice to be here.
Did I say that right, Fazl?
Yeah, Fazl's right. Yeah,
Okay,
there you
good.
go. You got it
I'm
right.
pretty proud of myself.
There you go.
Well, thank you very much for joining us today. And where are you coming from today?
So, Stafford, Texas, where
Nice.
it's a lot warmer and a lot more humid than up here, right?
Than a wintry Toronto today.
There you
right?
go.
And remember, it's Toronto.
Toronto.
There
All
we
right.
go. There we
All
go.
right.
Okay, you're now a Torontonian after that.
All right. There you go.
That's awesome. So maybe give me a little bit of background about yourself, what you do for Emerson, why you're here today.
Sure, yeah. So, my name is Mo Fazl. I am the current business development manager for PRV Monitoring and Downstream Tank. And it's a handful.
Yeah, big title there.
Right, big
you got
title.
the whole alphabet.
Pretty much, right? But yeah, so I'm here this week to help Lakeside with a couple of trainings
Nice.
around PRV monitoring and just overpressure protection seminar.
Great. That's awesome. Yeah, and that's where I thought, hey, this is a great opportunity to sit down. I need to learn more about PRV monitoring, so I may as well also learn about how PRVs actually work.
Yep.
So, okay, great.
We'll dive all into it.
Oh, I'm excited. So you've done PRVs your entire career at Emerson. Where'd you start out?
Yeah, so pretty much, right? So a little bit of my background is I have a bachelor's in mechanical engineering.
Great.
So I did that out in California, then moved to Houston and started working with Emerson.
Wow, all the warm spots.
Yeah.
And you're from Dubai originally?
Yes.
Okay, yeah. No snow.
No snow. I made sure of that.
Good.
So Houston started with Emerson. I started as an application engineer. So it's more
Great.
on the technical side of quoting, lead time, substitutions,
Yep.
all that good stuff. And then it's been about 6 to 8 months. I lose track of time. But since I've been in this position,
Oh, good.
So for honing in and focusing mainly on PRV monitoring and downstream tank. I've been with Emerson since 2019. I'm doing my MBA as well right now.
Oh, no way. Congrats.
Yeah.
That's awesome.
So hopefully you're going to graduate soon.
Yeah?
So,
Where are you going to school for that? In Texas?
in Texas, yeah. So UT.
Oh, nice. Okay. Part-time?
Yeah, professional. Yeah.
Oh, nice.
Yeah.
So
It's a lot of work.
yeah, I was
So-
going to say, how many years or?
2 years. So
That's a lot of work.
yeah. So towards the end of it, I'm counting days. Can't wait.
That's exciting.
Yeah.
I'm doing mine too, but mine's 3 years. So
Oh,
it's a
okay.
little bit longer. I
A
feel
little
like it's a
longer.
pretty standard pace.
Yeah.
Yeah. It's interesting, eh? It's a different perspective than engineering.
No,
right?
100%. So
Yeah.
I think a lot of that had to do with my joining as an application engineer,
Yeah.
where you get a little bit more exposure to both the technical as well as the, quote unquote business side of things.
Yep.
And that's what interested me and intrigued me to learn more about that because
Yeah.
I had the knowledge in
Yep.
mechanical. So MBA has been a great tool. I've already been able to use a lot of what I've learned.
It's cool.
So definitely loving every moment of it.
And it's weird to be in a program where they're not trying to fail you out.
Right?
They want you to come back and keep paying that
Pretty
tuition,
much.
right?
Pretty much.
You're like, where's this trick here? You mean I actually just have to apply what I've learned? And
Right.
Where's the trick?
It seems
right?
deceiving.
Yeah,
Right?
I'm so used to so I studied chemical engineering. And
Okay.
so, believe it or not, I always tell people this and they laugh. My worst subject was chemistry, and you'd think a chemical, but no,
Right.
there's hardly any. It's more like process engineering is what I think
Right.
the proper title is. But you say chemical, and everyone thinks it's like Breaking Bad, right?
Right.
And so I swear, chemistry. This has been my experience of chemistry. Is you learn, what happens 90% of the time, and generally this is what happens when these things mix together.
Right.
And then you get to the test, and it's like, well, we're actually going to test you on the 10% of the times.
10%.
Where no, that actually doesn't. Like it wasn't concrete. It wasn't 2 + 2. It's 4. It's like, well, sometimes it's 4. Sometimes it's 3.
Right.
Maybe it's 5 today. That's how I felt about chemistry. So,
Okay.
and then
That's
the,
really interesting.
the business side is even more like less. Well, what are you thinking? It's hard to know
Right.
for sure unless we try that, right?
Exactly.
And then quantify the.
Yeah, I feel it's better too because your group of like your cohort or your group of people that you're with is totally different as well, right?
Yes.
Like in engineering or when you're doing your bachelor's, it's everyone's trying to test it out and go their own ways.
Yeah.
But when you're doing your professional MBA, it's a bunch of different people in different places in life, all going towards a common goal. So I feel it's definitely a unique experience.
And a lot of people go to their undergrad studies just because they have to, right? They feel they have to.
Right.
Their parents are saying they have to. The norm says they have to. So versus, when someone's doing continuing education, it's they chose to do that. Maybe they're paying for it. It's all this extra time that they don't have, right?
Right.
You have a family or whatever. You're kind of like, what are you doing studying on the weekend? Right? Reading some case reports. And it's like, no, this is going to help me. I swear.
Yeah.
That's awesome.
That's what you tell yourself.
That's what I tell myself. Absolutely. Although it gives you an excuse to read things, about Tesla and say, no, this is relevant to what I need to know about, right?
Sure.
That's awesome. Okay, so and you grew up in Dubai?
Yeah.
Okay.
So pretty much born and raised there. Spent all my formative years there, and then moved out to California for school.
Gotcha.
Did 4 years there, loved every moment of it. Then moved to Houston, and I've been there ever since.
It seems like everybody's moving from California out to Texas, eh?
So it was actually not planned to be that way.
Oh yeah.
But ever since COVID and things have hit, everyone seems to be moving there. But a lot of people are moving back too because they don't like how the lifestyle is. But it's been a good mix.
That's awesome.
Yeah.
That's awesome. Okay, so let's talk about PRVs a little bit.
Sure.
Because I need to learn more about these. So first of all, what does it stand for, and how does it work?
Okay, so PRV is pressure relief valve.
Yes.
Right? So it's also commonly referred to as PRD, which is pressure relief device, right?
Okay.
So they're interchangeable. The only thing is with pressure relief device, more, I guess, devices come under that title, right? So it could be like a rupture disc, or it could be a pressure relief valve.
Oh, okay.
So depending on how it's being referred to, inferring it gets a little tricky.
That makes sense.
But as long as they say PRV, then they're definitely referring to a valve, right? So the way I think of a PRV is it's a complete mechanical device, right? So completely off-grid, no visibility, no electronics. It works on a basic pressure play, right? So it's all about force. So the way it works is, think of it as there are two different main types, right? One's a direct spring and one's a pilot operated. So your direct spring is you have a spring force pushing downward as a seating force.
Oh, yeah.
And then you have your inlet force, which is your system pressure.
Yes.
Right? So as your system pressure comes closer to a quote-unquote set pressure, which is what your spring is rated to, your spring starts to compress.
Gotcha.
Right? So then once you reach your set pressure, your spring is compressed enough to where the valve opens and your process is flowing through your valve.
Gotcha.
Right? So a good way I think of it is, think of it as a can of Coca-Cola or Pepsi.
Yeah.
Right? Now, say it's a pressurized vessel,
yeah,
right? Because there's carbon dioxide in it, there's liquid in it. Now, the external force is acting on it, right? It could be heat, it could be cold, and that causes some internal changes, right? Now, if there's no outlet for that internal pressure change, the can deforms.
Gotcha.
Right? It could lead to an explosion. That's the worst case.
Yep.
A normal case would be where it just deforms. But if you have a device on there that just lets it relieve as and when needed, it keeps the device the way it is, it keeps the process safe, and it just, keeps everything going smooth.
That makes sense.
Safety hazard and nothing, right?
Okay.
So that's essentially what a PRV is essentially used for.
I think of a pressure cooker, right?
Yeah,
I know.
perfect.
My brother-in-law loves to cook at a pressure cooker, and then it's always this terrifying thing that's going off, blowing steam. Hey, what's going on over here, right? Should I go unplug this? No, that's fine. That's part of the process. Okay, because the window is all fogged up, right?
Right, exactly.
That's where I always think of PRVs.
No,
right?
that's a perfect
cooking
analogy too.
Yeah.
Right.
Okay, that's pretty cool. Well, I'm happy to explain that about PRDs, because I always use those terms interchangeably. I didn't understand. But so when you're talking a ruptured disc, right? I guess the difference is that's a one-time use.
Yeah,
right?
so it's a one-time use device. So a ruptured disc, essentially, think of it as a disc that is essentially your last line of defense, right?
Yeah.
And once it ruptures, it's open. It does not reclose, essentially, right? So sometimes I've seen it used in industry where it's like at the end of, for instance, like a pipe.
Yeah.
Right? To where they don't expect it to release.
Gotcha.
But if it does, they want to be notified about it or something like that. So it's like a last line of defense to where they don't expect it to go off.
Okay. You wouldn't necessarily use it in combination with a PRV?
Yeah, so a lot of times you do, right? So
Okay.
it's below the inlet, or it's right at the inlet of the PRV.
Oh.
Right. So it's your inlet and then your PRV itself, right?
Okay.
So your rupture disc opens, but then you still want to regulate the exposure of that service to the atmosphere.
Gotcha.
Right. So that's where you could use a pressure relief device to where it relieves your system pressure, but it recloses as well. So it's not just open or exposed.
And to tie it a little bit into measurement, I think that's where we've seen you can put pressure transmitters between the rupture disc and the PRV.
Correct.
Maybe it's not at the point where the PRV is lifting, but it's at the point that's blown through the rupture disc. I guess they can be set at different points, right?
Correct. So it's the wireless pressure gauge, right?
Yeah.
So that goes right in between your rupture disc and your PRV.
Yeah.
To where it gives you notification on the pressure difference, right? So in standard operation, it'll be 0 because you don't expect anything between your rupture disc and your PRV because the rupture disc is shut.
Yep.
As soon as your rupture disc opens, then you expect some kind of pressure reading.
Gotcha.
So yeah, you don't have any visibility on the valve operation, but you do have visibility on the internal chamber being filled or not.
Gotcha. Okay. All this is starting to make more sense to me now.
Okay, great.
You know what? Let's take a quick step back, though, and I think we need to talk a little bit about why. Why do we even need PRVs? Where do they come in? Where do they fit?
Okay.
Right? Like, you know what I mean?
Right. So like I mentioned earlier, right? So there could be multiple applications. So in process plants, it could be around, certain applications called block discharge, external fire, power failure. So it's mainly 2 types of scenarios, right? One is where you use it as a safety, and one is where you use it as a relief, right? A lot of the valves that we have, Anderson, Greenwood, and Crosby, could be used as both pressure safety valves as well as relief valves. So depending on your atmosphere, in your setting, in your site, right? If you're using your valve to just relieve pressure every time pressure increases with process or thermal expansion, for instance, right? That's when you use a relief device. And a safety device is when you want it to open like 0 to 100 instantly when it hits that specific pressure, because it could lead to a catastrophic event across the facility, right?
Okay, for protection.
Okay. So essentially, they're used for pressure protection. So it falls under the umbrella of overpressure protection, right? So anytime the pressure exceeds a specific limit, and this could be very lethal, right? Because, when you think about it, a couple 100 pounds, 100 PSI, but if it's confined in a specific space and it explodes, or the service that it's used in, this could lead to like significantly like catastrophic events.
That makes sense.
So it's a safety device, right?
Yep.
That's its primary purpose.
It can lead into a bit of an efficiency discussion, though, too, right?
Yes.
Yeah.
So I guess a common phrase that one of the people I work with uses is a PRV is a compromise between safety and emissions, right? So it's like you want your safety, but you are inviting emissions with it. There's no real workaround around it until now. You have your product losses and everything tied to it.
Yeah, that makes sense because I'm thinking of a scenario where, again, tying it back to instrumentation.
Right.
So we have our level transmitters, and an option we have on the level transmitters is a purging system to clean off the antenna. So some applications are very dirty, right? Or there's a ton of buildup. So you have in this kind of air purge, so you can blow air in and it can clean off that antenna, and hopefully it cleans off and you can read an accurate level reading. But we had one customer who they were saying how they have, I guess it was their PRV was set to, something in the inches of water, right? It was a very, very, very small, I guess, pressure that they would have in the vapor space of this vessel. So they were asking me about the minimum pressure, or the minimum flow rate to clean off this antenna. And I'm thinking minimum. I prefer maximum. Right? Can we get 100 PSI? Like, we got to clean this thing off. And then I didn't realize. So what would happen is, now granted it is a big vessel, depending on how much vapor space, I think it would take a while to fill that up. But that was the concern, was they had their PRV set to something at the inches of water level.
Right.
And I was asking for 100, 125 PSI G to clean off the antenna. So it wasn't a good fit in that application.
Yeah. So I think that's a good point to focus on, I guess, a couple of the different styles of valves as well, right? So they do range from a couple inches water column all the way up to like 2,000 plus, 4,000 plus PSI. So depending on the application, so usually on tanks, we use our low pressure pilots, right? Or we have tank products,
Okay.
which are typically weight loaded. But your low pressure pilots would be ideal in terms of emission service, like, and then bubble tightness and basically sustainability, right? Like the emission side of it.
Yeah.
So they'd be perfect. They do go down to inches of water column.
Gotcha.
And they go up to, I think, they offer a combo of pressure and vacuum. Because like I spoke to you earlier about the Coke can, right? Now think of it as two pipes attached to the can.
Yep.
You're either pushing liquid in or you're pulling liquid out.
Yeah.
So when you're pushing liquid in, it needs to relieve that additional pressure, right? Because it's not going anywhere.
Yes. Yeah. You don't want to build up.
Exactly.
Yep.
So it's pressure relieving. And then when it's pulling, you don't want the can to cave in, right? Because you don't want a vacuum scenario, right?
Yep.
So you'd need something to like push air or like whatever fluid into this can,
place.
right?
Gotcha.
So there's a pressure and vacuum side to it too, and LPPs are offered with both.
Okay. And so we had talked a little bit about springs. You just mentioned weight. What are the different mechanisms for PRV? So I guess you can use springs and weights, or just weights.
PRVs are mainly, you have your direct spring and you have your pilot operated.
Okay.
Pilot operated is more of a force play. So the way it works is your main valve is attached to a pilot, which I consider like the brains of the operation, right? So your pilot has a spring in there, which is set on your set pressure. And the way the main valve is structured is you have an inlet and you have a dome. So dome is like a little bit area above the internals. It has a larger area than the inlet. So during normal operation, the dome and the inlet see the same set pressure. See the same pressure. Sorry, set pressure, right? So since the area is larger, it's tighter, right? The seating force downward, the downward force is strong.
Okay, yep.
And as you reach set pressure, it gets tighter and tighter because of the area on top.
Yeah.
And then once you do reach set pressure, the pilot vents out the dome.
Yep.
And then once that vents, the internals start to lift and the piston lifts and the valve opens.
Okay.
So it is kind of like at the end of the day a spring play.
Yeah.
But the springs in the pilot, whereas like in your direct spring valve, the spring's right in your bonnet, right? So it's right above the seating force, and the spring is the one pushing the seating force downwards.
Okay. So when you say weight, though, you're not meaning a physical weight. I'm thinking like something at the gym, right?
Right. So those are weight-loaded products for tank. So they're a little different. So they are actually weights. They are literally weights on there.
Oh, that's kind of cool.
They have specific capacities for those devices. And depending on when those set pressures are met in, I guess, conjunction with that weight, the device opens to relieve or, I guess, take in, right? So it's in, breathe, out. And those are mainly for tanks, right? So it's mainly in, breathe, or out, breathe of a tank.
Why is it mainly for tanks that they use the weight?
Because of the set pressure, right? Like, it really depends on, like, if you're going really low,
gotcha.
Then, it just makes more sense to have something like that rather than having
a spring
or like a really, because pilot valves are perceived as complex valves.
Interesting.
Depending on, how it's a little bit overwhelming for technicians to work on as well, unless they're exposed to the whole knowledge of it. So that's why it's just preferred for easier technology to be on there.
And so the spring is generally when you have higher forces or higher pressures, I guess?
Right, because on the lower pressure pilots too, like they use diaphragms.
Yeah.
Right. So it really just depends.
Okay. So there's a lot that goes into the spring then.
Yeah.
Okay.
Yeah.
And I guess that's really where, the spring and then I guess the actual chamber size, that's where all the engineering goes into when you're sizing?
Exactly.
Okay. And is there like risk that the spring wears out over time? Is that
so I wouldn't say there's a risk of it wearing out, but so what happens is when valves are pulled out of service, right? They go through a standard procedure where they're pre-tested before they're even taken apart. So it comes from the customer site.
Yep.
We test it from at its set pressure. We see how it performs, and accordingly, service is determined on it, right? So then, if you see it's opening way before set pressure, or it's basically not operating the way it's supposed to, then you do a little bit dive a little bit deeper to understand where it went wrong. Is it physical parts? Is it the spring?
Gotcha.
What do we need to do, and move on from there?
Okay, so it's kind of part of the standard operating procedure.
Exactly.
When you take the valves out of service, you test them.
You test them. Yeah.
So it's not like you're gonna this isn't going to happen overnight, right?
No,
This is just part of the standard maintenance.
Exactly, right? Like I said earlier, it's a mechanical device. It's used primarily off-grid, right? So it's been around since a very, very long time, right? And the reason for that is if there's a power failure or something like that, like these devices will still work the way they're supposed to.
Yeah.
Right? They will still protect the facility, make sure nothing goes wrong. And that's why with PRVs, preventive maintenance is really promoted highly.
That makes
right?
sense.
And Lakeside does it too, right?
Yeah.
Because that's what we recommend all our customers to do. Have valves on a specific maintenance cycle. It could be determined by multiple ways. And we could dive more into it with PRV monitoring too, right? Because that can help refine your schedule.
Yes.
But depending on the schedule you have and the age of the valve, when you pull it out, how you pull it out, you could determine accordingly.
Gotcha. Yeah, because I'm just thinking you could probably have the similar effect if you just use a pressure transmitter paired with like a solenoid, right? But then you have like this mini loop where the pressure transmitter, based on the pressure, then opens the solenoid to relieve. I'm thinking of a way to automate
it, but it gets difficult with sizes, with capacity, and there's a lot more that goes into it, right? Like you with a solenoid and pressure transmitter, it's still a lot of controls behind it, right?
Yeah.
Because when you see it, then you need the solenoid to happen. But then, for instance, like I said earlier, if there's a power failure, then
that's kind of what I was thinking was how else could you do this if it wasn't mechanical? Well, I guess you can make a little loop out of it, but what do you gain from that? Really, probably not a lot.
And if you compare, I'm assuming getting the logic and everything put in, it's going to be a lot more tedious than just putting a device in there.
More money, and now you have maybe 2-3 things you have to maintain versus this one. Yeah. Okay. Well, there goes that idea.
Yeah.
I thought I had a whole other market there to grow measurement. No, that's pretty cool. Okay. This is making more sense to me. I'm starting to understand it.
Okay.
Maybe you could take me back to your days of being an AE, which wasn't too long ago, it sounds like.
Yeah.
And can you talk to me about sizing and selecting and kind of what goes into that? You know, if let's say I'm a customer and I need a PRV for my tank or my process, right? Like what are the kinds of things that you need and what are the trade-off decisions that you're making?
Okay. So a lot of it goes to the vessel you're protecting, right?
Yeah.
So you need to work with basically the maximum allowable working pressure of your vessel.
Yep.
Right? You need to understand your service. You need to see what kind of pressures could reach under worst case scenarios. So you size for multiple scenarios.
Okay.
It's not just, you take one and you size based off of that. Size for multiple scenarios to see and understand what the valve is going to see, right? Or what the device or service or process is going to see. And accordingly, you size your valve to help relieve that capacity, keeping in mind the piping dimensions you have and go from there, right? It could really range from the different applications or different cases, right? Like a block discharge or power failure.
Gotcha.
So it really just depends on that. But in terms of sizing and selecting, you need to understand your property, your fluids, the sizing case, the capacity required, set pressure, which is determined by, the maximum allowable working pressure of your vessel, and then the codes and standards that apply to that business, depending on where that business is as well.
So I'm thinking it's probably, I guess, it's no different than picking instrumentation, right? You got to make sure it's compatible is the biggest one, right? What's in that vessel? Is it some sort of nasty chemical, right? You have to make sure it's the right material.
Exactly. And it's a similar thing on the PRVs too, right? So we offer certain standard materials which could be used with majority of the processes out there. But then depending on specific services which could eat through these normal metals, we need to offer like exotic trims or exotic materials to help, for it to be reliable in that service.
Gotcha.
And same goes for like, I guess, soft goods on the pilot valves as well.
Yeah.
Right? So as it sees it, accordingly you determine. So like I said earlier, once you know your process and the process conditions, you have a whole material compatibility thing you look at as well to help figure out what's the best.
But then surely some applications require a faster response or a more accurate response than other. Are there different selections that you make to impact that?
Yeah. So like I said a little bit earlier, right? So the safety versus relief scenario. For safety, you want it to 0 to 100 real quick, right there and then once it hits that set pressure.
Yep.
So under pilot valves, you have two different types. One is a snap-acting pilot and one's a modulating pilot.
Okay.
Right? So you can think of your modulating pilot as a regulator, right? Opens proportional to the relief event. Okay. So if your overpressure event is such that it requires the valve to only be open 10%, your valve only opens 10% and then closes back down. So that way you don't lose as much as of your product.
Gotcha.
But if you're looking at a safety event where you needed to relieve the 100% of the capacity as soon as set pressure hits, your snap acting is a good option, because as soon as your set pressure hits, it goes from 0 to 100 and just relieves all that pressure out.
That makes sense. Okay.
Yeah.
Yeah. So because you don't want it, exactly like you said, just be full open and you're letting way more out than you need to.
Exactly. Like if you think of it in terms of like natural gas processing, right? Natural gas is a very expensive commodity today. And say if your valve opens 0 to 100 when it just needs to be open 10%, you just lose and all that. Essentially, it's money, right?
Yeah.
That you're losing out there.
Yeah. Would you have multiple PRVs in a vessel, or is it?
Yeah. So depending on the tank size and depending on the required capacity, you could have what they call a multi-valve selection, right? So your capacity is so high that where one valve by itself will not help relieve that whole pressure capacity, right? So you have multiple valves at staggered set pressures. Not all of them open at the same time.
Okay, yeah.
They're staggered off a little bit, and then they open essentially to relieve that pressure. And it's sized again for worst case, right? So maybe you could have, and there might be a true application. Maybe you have a really big tank with 16 valves on there.
Yeah.
Right? But maybe only 4 of them operate every so often. But one worst case scenario comes where like all 16 need to work.
Yeah.
All 16 open.
And I guess the other thing too, I guess this kind of makes more sense. Like if one PRV to be able to handle that versus 16, right? Like that would be a really big PRV possibly too, right? With a lot of cost.
So it depends, right? So now if you're going to multi-valve, you have the option to play around depending on how many outlets you have available, what's your installation like, what's the customer preference. Do you want 8 valves? Do you want 4 valves? Do you want,
Yeah.
like depending on what they want, like maybe you could do 30 valves, but really small size.
Yes.
Right? So more maintenance, more things to check on, more things to look at. But it all comes out of the capacity play, right?
Yeah.
So each valve has a rated capacity.
Okay.
So you need to make sure that those rated capacities work with your what's required for your vessel.
That makes sense. And then you said from an installation perspective, like again, when I'm thinking level transmitters, I'm thinking what kind of nozzles they have available. What are you looking for in a vessel? Same thing?
So it depends. So in terms of tanks, yes. In terms of processes, usually it's piping. So piping sizes, right? Some customers come to us if it's a new skid being built, then they determine the size based on the PRV that they have. They want based on the capacity, and then they give us the information. But if it's a replacement, then they already have piping created, the size is already determined, so we need to work a little bit around that. And if there's no workaround, they need to consider piping changes, which is significantly expensive.
Okay, that makes sense. Yeah, because I keep picturing PRVs with tanks. So I wanted to talk a little bit more about piping.
Yes.
I guess you would use it for the same reason, right? You don't want to overpressure that piping.
Exactly, same reason, and it's usually across the whole facility, right? Coker units, your normal units, your significant. They'd be across a site without you even knowing about it, if that makes sense. It's so rudimentary. And
it's just part of the...
Yeah, it's pervasive, right? Across the whole facility, you will find it in each and every different unit. Because every unit has a safety requirement for it to be protected against a overpressure event. Because if it's not, it'll more often than not lead to an explosion.
Yeah, because it's all part of that pressurized system, right? And so I guess it doesn't matter if it's liquids or gases. There's going to be PRVs throughout it. Okay, and now this is a good question. So would you say there's more PRVs in that piping system than there are in the vessels? Because there's only so many vessels per site, depending on the site?
So more often than not, and I might be wrong on this, right?
That's
this
okay.
Is based
we
on
won't hold you to it.
Yeah, as my exposure, PRVs are usually, the end connections are pipings, not directly like a vessel.
That makes sense.
If it's directly a vessel, it'll usually be on tanks by itself, standalone. But it's mainly pervasive in plants, and plants usually have pipings associated with it.
And is there really anything special you have to do to install that PRV, or it's just, connection, marry it up like a flange?
Yeah, so there are flanges on it, right? So you need to make sure their flanges are rated to what's required of the application.
Yeah.
And then once that's done, it's pretty simple
Away
installation.
you go.
And we always recommend the techs be trained and they know what they're doing. And as long as that's the case, you're usually fine.
Yeah.
And most of the techs are usually trained on it because, again, these devices have been around for a while.
Okay. But so it's pretty simple, I guess, compared to, like, I think in flow meters, there's...
there's no calibration or anything like that, right? So, because everything, it comes pre-tested, it's ready to go in,
just install it.
and you just install it. Again, depending on the application, sometimes you don't want your pressure relief valve, operating. Right?
Yes.
You don't want your safety valve to go off, because that means a worst-case scenario in your site.
Yeah.
But that's why preventive maintenance is so important, right? Because that device could be out there for 10 years and you don't use it. And if you don't service it, the 11th year you need to use it, you need to make sure it operates the way it's supposed to operate. So that's why we recommend preventive maintenance schedules. And
that makes sense.
And they do that in their turnarounds that they have at plants. So, yeah.
I guess the only thing to watch out for is don't have anything on the outlet side, right? Or
So,
yes and no?
Yes and no, right?
Okay.
It could depend. There's some customers who relieve the atmosphere, right? So they're, okay, yeah, fine. There's nothing in the outlet.
Mm-hmm.
But the others, it could go to, a vapor recovery unit, for instance, right? If it's corrosive gas, they don't want it out in the atmosphere. They want to pipe it away somewhere. So there is piping.
Interesting.
On the external, on the outside of it. If it's expensive product that they're releasing because of an overpressure event, and maybe they want to get that product recouped somehow with the other, they do have.
I guess piping makes sense, or if you want to redirect it somewhere. I guess what I was thinking in terms of, I always thought, can't you stick a flow meter on that to monitor how much comes out? But I was always told that, well, if this is for a safety system, you really don't want to put anything that might restrict this ability to relieve pressure, right? There are risks with that.
100%.
It probably wouldn't be a very good flow measurement too. You'd have like a single shot of a lot of flow and...
Yeah, because again, it's a burst, and depending on the size and capacity, it could be a lot of force too, right?
That's a good point.
And then again, if you would, you'd have to do something with the piping, and then do you really want to mess with your piping when it's a safety thing? So it's just easier.
Okay.
Not to, but that's where PRV monitoring comes into play too, right?
So would you get involved at all with, I think they're called anti-surge valves? Is that kind of related to PRVs, or is that over here?
Educate me a little bit about that.
So this is, I saw this at the exchange. That's why I brought it up. And I swear it was right beside where I saw the PRVs. And it was this giant, massive fissure valve. And, this thing kept opening every minute. I think they were showing a big demo for how this, I don't know, maybe it was a 3-foot or a 4-foot valve. It was massive, and just how fast this thing could open. And I think the application was protecting a compressor. So if you have back pressure come through the line, you don't want the back pressure to go into the compressor. You want to then divert it away. So I'm thinking probably not. I don't think it's be considered a PRV, but it's pressure protection for, I guess, a compressor was this application.
Okay, I might need to look more into it. Okay. It's the first I've heard of it, but it sounds like a pretty cool device.
Yeah, it was. Well, it was this massive thing, and then it got me closer to the PRV. So then I started talking to the PRV folks. I thought, okay, well, hey, it did its job, whether it was related or not. I went over to see the big valve, and then I saw the skid that I think you had built to showcase all the different PRVs in action. And so that's really cool. It's a good piece to have to help educate and make people are aware of the different options out there, right?
Right. So that's where we're using that. We call it our monitoring skid, but essentially it's a skid that can be used for anything.
Okay.
To display essentially how a PRV works, or how a valve operates. Because a lot of times, it's very you don't want to see these valves operate, like I said earlier, right? Like if it's a safety scenario, you don't want it to go off anything. But it's difficult to visually understand how a valve works. So how does it pop, or how does it open, right? But so being able to do that in the demo really takes the message across, right? And we have our monitoring devices attached to those PRVs.
Yes.
And we have a computer screen out there which displays how we pull the information, what information we get, and basically more visibility into the operation of the valve.
Yeah, and happy you brought that up. That kind of segues into a nice next topic, which is the PRV monitor. And I feel like that's a big piece that people have been very focused on recently. It's, it's, yes, we need PRVs to protect our process, but well, what is coming out of that valve, right? Is it some sort of toxic or, combustible? And is that going to atmosphere? And if it is, how much?
Exactly.
Right?
Exactly.
So how do you do that?
So there are different ways, right? But a little bit about why PRV monitoring is so important, because you touched based on it, is like you said, the way I look at it is there are 4 major buckets that it solves, or 4 major problems that it takes care of, right? These devices were off grid and you had no visibility on how it operated.
Yep.
But now we're giving you a way to understand how they're actually operating, right? Is it opening when it's supposed to open? Is it flowing? How much is it flowing? What is the process of what's going through it, so you can see how much is being pushed out, where, depending on where it's going, right? So currently the EPA in the States has been putting a lot of mandates on valves in hazardous air pollutants that are went into the atmosphere.
Okay.
Right? So they've been kind of honing in on this to help us analyze and determine how much is being put out there. Because again, these are harmful to humans, and it could be lethal service that could it could really harm a person.
Yeah.
So emissions or sustainability is one of the biggest buckets, right?
That makes sense.
The other one's productivity. Like I was talking earlier, if it's LNG and you have your valve that's opening constantly, it's quote unquote not sized right. It's oversized, undersized. It's chattering, which is opening before it's supposed to, or like just opening and closing constantly.
Very fast.
Yeah.
Like chattering teeth.
Exactly, literally, right? So which damages the seating surface. And because of that, leakages are possible, right? So when that happens, you're losing expensive product. You put all this money into like processing it and making it into pure for storage.
Yep.
But while it's going to storage, it's just leaking out there, right? And then you have reliability, which is getting the most out of your asset, knowing your maintenance cycles for your PRVs to make sure that they're sustainable, they're working the way they're supposed to, they're not leaking. And then the last bucket is safety, right? Depending on certain, for instance, like NACE applications. NACE is like lethal service, right? Like H2S gas or something like that. You want to know when those valves are going off, depending on where they're piped away or how they're discharging, where they're being discharged to. You want to know because those are heavy gases, right? So say, for instance, I don't think anyone does this. I hope no one does this. But if it is open to atmosphere or something like that, and that valve discharges, right? It's a heavy gas, so it settles. So if it settles, and it settles to like where people are walking around,
pool of it,
that's,
right?
Yeah, that's that could be catastrophic for someone's health. It's lethal. So it could take life.
Yes.
Right. So having monitoring gives you visibility of your PRV to understand either one of those 4 buckets. Right. There's a major push on the first and the second, which is sustainability and productivity. Right?
Yeah.
So you're able to know how much you're losing, if you're losing. Because, again, it's called, quote-unquote, product loss, because when your valve is relieving, it's relieving what's in the system.
Yes.
And that's usually product, right? So there are a couple of ways to do it, right? The first is we use a Roseman Acoustic 708 transmitter.
Yep.
Right? This is a wireless ULI device, like you know. It's usually strapped on the outlet, easy installation. It's non-intrusive, so it doesn't really change the PRV, right?
Yes.
It goes in the outlet. We recommend to use it with Plant Web Insight because it helps with your baseline. It helps with the algorithm.
Yeah.
There's less, logic that needs to be programmed on the back end, on the computer, on the customer side.
Yeah, that makes sense.
To basically pull the data in and understand it better. But what that basically does is it lets you know when it opens and when it closes, right? Through that period in time, be it 1 minute or 5, you have to assume 100% open.
Yes.
Right? But the caveat there is valves usually are not that way.
Yeah.
Right? Valves usually don't operate like it hits set and it opens 100 and it closes down. There is a gradual buildup, right? Think of it like a mountain. So it's a little gradual buildup, then it reaches full lift, then it reaches some kind of an equilibrium, which is on the downward end, and then it shuts back down, right? So to be able to better understand that tracking, that reflects big time on how much you're either reporting or you're documenting. So it could be multiple ways, right? So for that, for direct springs, what we do is we have a Fisher product that we use. which attaches itself to the spindle, and the spindle is also commonly known as stem, right? So that essentially tracks how much the valve is lifting, right? So once you know how much the valve is lifting, you're able to actually trace that graph a lot better. So you have a better accuracy of how much is being emitted in that pressure relief event.
So you know where the spring is, and then based on where the spring is, you calculate, or you know how big the bore is, or I guess how much.
Yeah, so
area?
you know, they're again, these are rated capacity valves, and we have the clearances and measurements, right? So we are able to correlate like vertical movement to lift.
That makes sense.
So once you're able to do that, then you know that okay, the valve is open at 10% for this period
for
of
this
time.
duration.
So you get better accuracy of how much is being pushed out there.
That makes sense. Yeah, because that was kind of the limitation that I wasn't really aware of these solutions, and so I always thought about, well, we have our wireless acoustic device, which is great because it's wireless, right? Which is a huge advantage. You don't have to, especially if it's on a tank, right?
Right, 100%.
To get wiring out there, and then it's listening for if there's any product coming through that outlet, but which is a big improvement over not knowing anything.
Agreed.
Right?
So it's a step in the right direction, but every technology comes with limitations, right?
Yes. Yeah.
So if it's like too low set pressure or something like that, like being able to generate those enough acoustic counts or enough turbulence in a pipe for it to be recorded with a temperature delta or temperature difference, that leads to a little bit of a gray area. But again, like you said, it's more information than no information.
And it's funny, I keep pulling it back to measurement. Sorry to do this to you, but so I almost think of it in a way as, in a vessel, we have a level switch and a level detector, right? The switch is going to, trigger on or off, right? Like, am I touching product? Am I not touching? And the level transmitter really is going to tell you, well, where that level actually is. Exactly. It almost might be a very similar analogy where the 708 is the switch. Do you have product coming through here or not? Right. Now, if you want to quantify that, well, maybe we need to be a little bit more precise with some of these other solutions out there.
200%, right? Like, so it goes back to it like you probably know this better, discrete and analog, right?
Yeah.
So the 708 is a discrete solution. It tells you on, tells you off.
Yeah.
No other information between. But your other solutions that we have, like the one with Fisher and the direct spring, it gives you more of an analog understanding of actually how much, right? So you're able to get a better quantification.
That makes more sense.
And then on the pilot valves, we have what I consider our best technology so far is we use a differential pressure transmitter. Yeah. Which actually accurately tries to tell us lift percentage on a pilot valve. Right. Now, when you combine that with something like your 400 series or your modulating pilot with Anderson Greenwood, your modulating pilot only opens as much as it needs to, right? Proportional to the overpressure event. And the way that the differential pressure works is it takes the difference between the inlet and the dome, correlates that to lift percentage. Right? Oh, okay. And since we know their capacities and things like that, we're able to correlate that to flow. Yes. So we actually are able to get flow from a modulating pilot because it accurately opens proportional to the overpressure event. Yeah. So that makes sense because it's no different than calculating because you have the pressure, you have how big the opening is. Okay. And the other technology, sorry, what was that one called where it wasn't? You said it can directly tell how much the spring has lifted. That's for a different type? It's a spindle lifting. Okay. That's on your direct springs, right? So it's similar information, but one's on a direct spring valve and one's on a pilot operator. Right? Okay, so they're both doing similar things, but it's a different PRV, so you need a different solution. Correct. Okay, so this is where I saw the Roseman pressure transmitters on that skid. This is exactly what they were doing. Exactly, right? So the recommendation is depending on service and how critical it is, depending on the size, depending on the lethalness, if that's even a word, of the service, right? Yeah, probably. You'd prefer a pilot because it only opens as much as it needs to. Yes. And you get your information. Now, on the flip side, if it's expensive process, again, you'd prefer a pilot because you know how much it opens. It only opens as much as it needs to, and you get all that accurate information. Okay. Now we're getting somewhere. So pilot and... What was the other one? Spring? Direct spring. Direct spring. Pilot, direct spring. Are there any others? This is the main two. What's slam shut? So slam shuts are regulators, right? Oh, so okay. That's like a whole different division, right? Okay. So slam shuts, basic concept of it is once it reaches a specific point, it literally slams shut. So it's like opposite of a PRV? Yeah.
Okay. All right. That's a whole other
I think
discussion.
like opposite of like a rupture disc, right? You
Yeah.
can think like when it reaches a certain pressure, it opens. This one, when it reaches a certain pressure, it closes.
Does it ever open again?
I think that's a good question.
Okay.
That's a good question. But the way I see that being used is more in utilities, right? So like older cities like New York,
Yeah.
when you have natural gas or whatever being pushed in for utility purposes, and it exceeds a certain pressure before that causes any further like issue, you just shut it right there.
Yeah,
but I think it's used together with a loop or something. Again, I'm not an expert.
That's fair. I'm thinking like even my furnace at home, right? You don't want to over that or anything other part of the house, right? You don't want to give it too much natural gas. That would not end well.
Right.
Okay. Sorry. So getting back to the PRV monitoring, I think we're getting somewhere. These are starting to make sense to me. There was a term that they kept talking about, which was called a bellows.
Yes.
What's a bellows? What is all that?
So your bellows are mainly used near direct spring valves.
Okay,
right?
direct spring.
So the reason you use a bellows is when you have back pressure.
Gotcha.
Right? So it's difficult to visualize without like an actual schematic. But if you think of a schematic, you have an inlet, you have a body that essentially is connected to your outlet.
Yep.
Now, if you have back pressure in there, that back pressure is going to affect your internals.
That makes sense.
So it's gonna add additional downward force to your seating force.
Yeah.
Right. So basically, what you do is in those situations you use a bellows, which helps kind of isolate it and still make your set pressure the way it's supposed to. So it doesn't tamper with your set pressure based off your back pressure.
Okay.
So you use bellows in those applications. Now, about most of the bellows installations are done where there's a flare system, right?
Okay.
Because when you have you have a bunch of lines going through a common flare header.
Yes.
There is back pressure bound to be there.
Okay, that makes sense.
Now, another thing to note as well is flare systems are usually used with lethal or really corrosive gases, right? Like flammable. So, basically stuff you don't want getting out there.
Yeah.
Right. Now, another thing as well is when you use bellows valves, your bonnet, which is a part of your direct spring valve, has a bonnet vent.
Okay.
That vent needs to be open with bellows, because if not, then you essentially have a pressurized chamber, right? So whenever your spring compresses or moves, then you're going to have a pressurized chamber, which you want that pressure to be relieved. So you're going to have to have a bonnet vent open. Now, the issue there is your bellows are mechanical devices, right? So it's metal. Over multiple cycles, right? This metal fatigues because it goes through multiple, compressions essentially. And once this metal fatigues and it breaks, or it could be a pin size rupture, it could be a swell, it could be like multiple different things. But once it does break, all your back pressure lethal service goes through your bellows, up the bonnet and out the bonnet vent. Right? So essentially you're exposing that lethal service into the atmosphere.
Yeah, defeating the whole purpose.
Exactly. It's a form of fugitive emissions.
Yes.
Right? There have been situations in the past where it's been flammable and there was lightning and it caught fire.
Oh, wow.
And it caught fire at a facility. Holy. Right?
That's scary.
Yeah, right. So there are a lot of different, it can lead to really catastrophic events, right? One of the issues with that is you have no visibility into your bellows.
Yeah.
Because it's inside this closed, metallic piece, right? It's inside your body. You don't know it.
You can't measure it.
Exactly. So when you pull them out for service, that's when you see it.
You can check it then.
Exactly.
Okay.
So preventive maintenance is, again, like we said, it's
always going to be key here.
Exactly.
Yeah.
Right? So that's your basis for your bellows. But now, if you have a valve on 3-year maintenance schedule, right? And then you pull it out after 3 years, and you've seen your bellows has failed, quote unquote, right? So there's a hole or there's something wrong with it. Yeah. You don't know when that started. You don't know that was at month 20 or at month 30 or at month 6.
Okay.
Right? So your valve could have been leaking for all that time without you having any kind of visibility.
Okay.
Right? And then when that happens, it even compromises your set pressure.
Yeah.
Right? So your valve could open sooner or later. You don't know.
So is this the reason to use really a pilot operated versus
not necessarily
direct spring? No.
bellows have good applications. You
Yeah.
know, they're in the industry for a reason.
Yes.
Now there are certain applications where you can interchange one or the other,
Gotcha.
but you still need bellows valves at the end of the day,
Yeah.
depending on certain temperature limits, certain material compatibilities and such. So basically where bellows leak detection comes into play, right, is it consists of two components. One is a backup piston, which has been around for a while as well.
Oh, yeah.
So that's what increases the height a little bit. And it keeps your valve balanced against back pressure.
Yeah. Okay.
Right? So that way your valve still operates the way it's supposed to. There's no issue at all. And what we do there is we have a transmitter, right? A pressure transmitter, standard pressure transmitter,
Yep.
which helps. So once you have that backup piston, between your bellows and backup piston, it should see zero pressure.
Yep.
Right? It shouldn't see anything when the bellows is fine. But as soon as your bellows ruptures, up to, I think, point thousandths of an inch, right? That pressure transmitter can instantly detect pressure within that chamber,
Yeah.
right? So you know instantly that your bellows has failed,
Gotcha.
right? And then what it does is your backup piston balances your valve against back pressure, so your valve is still operating fine. You don't have any safety hazard or issue over there. But the backup piston has certain clearances. We know those clearances, and basically what those clearances do is up 90% and more, is depending on size, is what it restricts that flow of fugitive emissions out the bonnet. So you're limiting how much is being
Actually
pushed
can
out.
get out.
Exactly.
Okay.
And since we know the clearances, and since P1 we get from the transmitter, P2 is atmosphere, we're able to calculate how much fugitive emissions you're pushing out there depending on the size of the rupture in the
This is
bellows.
definitely what I saw at the exchange. That piece of it,
Yes.
because that's where I saw the pressure transmitter as well. Okay,
Yeah.
so this is a way that you can improve upon maybe the standard design of a bellows, right?
Exactly.
Okay.
Because there are going to be certain applications where you just can't get past the bellows,
Yeah.
right? So having this gives you that visibility of instant notification of when your bellows is ruptured.
That makes
for
sense.
for you to be more proactive and preventive about it, right? You could have a couple of bellows on the shelf, meaning you could have stocked them in your service pool. As soon as this happens, you pull it out, swap it out, put it back in there, you're done. You're good to go.
And thinking about the function of the bellows, right? For the back pressure, kind of offsetting that back pressure. It reminds me of a differential pressure transmitter for level measurements, where basically a similar idea is in a vessel, you're trying to measure how much liquid you have typically, right? And you have all this head pressure, that vapor pressure. So the DP transmitter is going to really offset. It's going to measure it on both sides, cancel each other out. The bellows is almost doing something similar, right? It kind of so that the PRV really is unimpacted by that head pressure or the back pressure, right? So okay, there's way more analogies between what we do day to day.
100%.
Okay.
Yeah, most definitely.
I see it.
I think another technology I'd like to highlight here is the diaphragm, right?
Okay.
So this is a I'd say new to the world technology, right? That you've just come out with on the Crosby J series.
Okay.
Where you in place of a bellows, you can use a diaphragm.
Okay.
So what that does is, your internals change a little bit, but you can use your diaphragm for up to higher percentages of back pressure.
Oh.
So right now your bellows goes up to, I think, 60% offset. With your diaphragm, you can go up to 80% offset.
Okay.
Right? So you're able to use it in a lot more applications. Currently, it's not going to eradicate the whole bellows market.
Yeah.
Because there are going to be certain temperature limitations, certain material compatibility limitations, right? But for your day-to-day, putting it in there, because bellows could be expensive. It's a metallic part. Standard material is Inconel. Inconel is expensive material.
Really? Wow.
Whereas using your diaphragm, every service turnaround, you could just swap it out, right? Because it could be part of your regular maintenance package or regular maintenance parts that you service.
Gotcha.
So that's another new to the world technology.
That's really cool.
That we can talk more about.
Yeah,
right?
yeah.
But yeah, I just wanted to throw that out there.
Yeah, it's good to know that there's options when it comes to that. And then ultimately, I think quantifying really is the biggest driver. I think, like you're saying. So no matter what the solution is can we quantify how much is coming out of that? And again, actually, I saw a video during the presentation at the Emerson Exchange where I didn't know. I don't know if they do this in Ontario, but they do it in Texas where they have helicopters that fly over some of these facilities. And I don't know if you have this in Texas, but we have red light cameras here.
Okay.
So if you go through a red light, it takes a photo of your license and it sends you a ticket in the mail. And they basically described it as a similar thing where they have these helicopters. And I don't know, I guess if the EPA or whoever does this, they fly over, and I think it's an IR camera.
Yes.
And if they see the vapors escaping these vessels, they take a photo and they send it to whoever it is, whatever refinery, and say, hey, here's your invoice for, your emissions. And
yeah,
that's so crazy.
Yeah, so the way the EPA works is a lot of it's self-reporting, right? So you need to be able to have a good estimate of these values, because now again, this is a little bit more into how the whole EPA works and the system works out there. Say for instance, you overestimate, right? So open, your duration of 5 minutes, you assume 100% open, you report, you keep reporting. Eventually, I'm assuming after one point, it's going to lead to some kind of fines, right?
Yeah.
Because you're putting out way too much than how much you're supposed to be putting out.
Yeah.
Now, say you have multiple of those fine scenarios, and what's going to happen is you're going to reach a consent decree. What a consent decree is essentially it's the EPA getting together with that site, with that company, figuring out that this is the amount of emissions being put out, this is the amount of fines you've paid. Now you got to spend a fixed specific amount in adopting, EPA compliant measures across the site.
Oh, okay.
So those could be really costly, right?
Yes.
And those consent decrees are in like millions.
Yeah.
Right? So it's like 20 million, 25 million, 15 million. Like you need to invest that amount of money in your site, across your sites to comply with certain things, right? So being able to accurately report accurately even get that data for yourself is crucial, because you need to know how your valves are operating, how your process is working, if everything's working right or wrong. And that data just gives you more insight into better optimizing your system.
I guess the other piece too is, let's say, if you don't know if it's opening or closing, I assume you probably have to assume some sort of duration, right?
Exactly.
Do you have to assume an hour, 2 hours, right? Like depending on where you are, I guess in the industry, it impacts that.
Right.
So it's going from, well, we don't know if it's open or not, to, well, we're assuming 1 hour, to, well, it's about 5 minutes, to now getting more specific depending on the solution.
Exactly.
And I guess ultimately, it depends on the severity of the application and criticality of it. Right. But I can see how this can become very complex and sophisticated from just a simple little PRV maybe from what it was decades and decades ago.
Right, 200%, right, and that's just one aspect of it in terms of sustainability. But now, if you think of it in terms of just process in general, say you own a site, for instance, you want to get the maximum throughput through your site. But you have these devices which are relieving. You want to know when they're relieving and how much they're relieving to tweak things around to get the most out of your process, as well as not have to worry about dollars flying out away.
Yes. Yeah, exactly.
Right? So again, there's a lot of nuances to it. It's going to depend from customer to customer. It's going to depend, from wire to wireless, from technology to technology, from valve to different valve type. But our focus is to help get the best of what's out there. And help get the customer what they want. That's what it is for measurement too, right? It's look, we have a ton of tools in the toolbox. Right. What can we help you with, right?
Exactly.
Help make your life easier.
Yeah, because every solution doesn't have to be this, very complex and sophisticated. Exactly. Some can be much simpler than others. There's nuance to what we're doing.
Exactly.
Well, great. This has been a really informative chat. I've learned a ton, Mo, so thank you very much for being on the show. For the listeners, if they want to learn more about PRVs, maybe they want to connect with you, where can they do that?
Sure. So, feel free to connect with me on LinkedIn.
Okay.
My name is Mo Fazl. It should be available on LinkedIn with Emerson. You want to know more about PRVs, feel free to reach out to either me on LinkedIn or reach out to your local partner, Lakeside. They have a very knowledgeable group of people out here. They'd know everything to help take care of your needs. So
great.
Definitely recommend these two resources.
I appreciate that. Well, thanks for coming out, being on the show. I really appreciate it as always.
Yeah.
And, until next time.
Sounds good. Thanks for having me.